Imagine electronics powering themselves just from the air. No batteries needed. Sounds a bit out there, right?
It really does, but it's becoming reality.
Today we're diving into radio frequency energy harvesting, or RFEH. We want to get past the simple diagrams.
Right, look under the hood at the real engineering, the complexity.
Exactly. What actually works? What are the trade-offs?
Yeah.
Our mission here is to give you a shortcut, really, to understanding how these self-powering, battery-free devices work, especially the low-power ones.
Let's get into it.
Okay, so first up, what exactly is RF energy harvesting? Could you break that down simply?
Sure. Basically, it's about grabbing those electromagnetic signals that are just everywhere. Think Wi-Fi, your phone signal, TV broadcasts.
All that invisible energy.
Exactly. And converting it, turning it into usable DC power for a device.
So it's a completely different way to power things, moving beyond batteries or plugs. Sounds ideal for IoT, maybe medical devices.
Precisely. That's where the big potential is. Think self-sustaining sensors, tiny implants. But here's the thing. The basic idea, the schematic, might look simple, but making it work effectively, that depends on really understanding each part.
It's not just if it makes power, but can it make enough reliably from these weak signals?
That's the core challenge. Absolutely.
Okay, let's break down the parts then. First, that antenna, that single-turn large loop antenna. Why large? What's the significance there?
Good question. That large is key. It's not like the tiny loops you see elsewhere. Its size, the perimeter, is specifically designed to be around one wavelength of the frequency it's trying to catch.
And they make it
much more efficient. It gives it this two-lobe radiation pattern, kind of like a dipole antenna.
So it's better at grabbing those signals.
Significantly better. If you stand it up vertically, you can get about 1.5 dB more gain in certain directions compared to a standard dipole. That's a real boost when you're dealing with faint ambient signals.
Okay, so the antenna grabs the wave. Next up, the rectifier bridge. That sounds like where the magic happens, turning AC into DC.
That's right. It's the heart of the conversion. And it's tricky at these super low power levels.
Why is that?
Because you lose energy in the conversion. You need really efficient diodes. Low barrier Schottky diodes are the standard choice because they turn on with very little voltage.
Makes sense. Minimize losses.
Exactly. And here's something cool. Newer designs are getting smarter. They don't just rectify the main frequency. They also harvest energy from the harmonics, those kind of signal echoes at higher frequencies. And doing that can boost the overall efficiency by, well, figures show over 25%, squeezing out more power.
Wow, okay. That's clever. What about the capacitors in the diagram? There's usually two, right? 6-block and count.
Yep, both essential. 6-block is basically traffic control. It keeps the AC signal from the antenna separate from the DC power going out, make sure the rectifier does its job properly.
And the gals you do their pros at?
That's the energy storage tank. It smooths out the DC voltage, but more importantly, it collects energy over time.
So if the RF signal is weak or intermittent?
Right. It stores up little bits of energy until there's enough for the device to do something, like send a quick data packet. It helps solve that cold start problem powering up from zero.
Got it. Okay, antenna, rectifier, caps.
Yeah.
But I've heard there's often a missing piece in those simple diagrams, something crucial.
You're absolutely right. This is a huge point. It's the impedance matching network, the IMN.
Impedance matching. Why is it left out of basic pictures?
Probably simplicity, but it's a critical mistake to ignore it in a real design. Without matching the impedance, the sort of electrical resistance between the antenna and the rectifier,
what happens?
A huge chunk of the energy the antenna does capture just gets reflected away, bounces right back off. You could lose like 90% or more.
So the whole system barely works without it.
Pretty much useless, yeah. The IMN ensures that maximum power actually gets transferred from the antenna into the rectifier. It's absolutely vital.
Okay, so assuming you have all the parts, including the IMN, what kind of power are we realistically talking about?
Look, it's generally low power, milliwatts, maybe even microwatts. But often that's enough for these ultra-low power sensors and devices.
But the range must be a big factor, right?
Huge factor. Physics is tough here. The power drops off fast with distance. It follows that inverse square law. Double the distance, you get only 1/4 of the power.
So a Wi-Fi router is only good for very close range.
Yeah, maybe up to 20 centimeters, something like that. But a big, powerful source, like a TV broadcast tower, that could potentially power a tiny device maybe 10 kilometers away. Big difference.
Wow, 20 centimeters versus 10 kilometers. That's massive. But designers aren't powerless, right? There are things they can do.
Oh, definitely. While you can't change physics, you can make smart design choices. For instance, data shows boosting antenna gain, say from 1 dBi to 6 dBi, can cut the charging time needed by over 60% at that 20 centimeter range.
Okay, so better antenna, faster charging.
Yeah. Or, if you control the source, even a small bump in power, like going from 14 dBm to 17 dBm, can more than halve the charging time at the same distance. So yes, engineering choices matter a lot.
This is where it gets really practical. What are people actually doing with this tech now? Where are we seeing it deployed?
We're seeing it in wireless sensor networks, especially in places that are hard or expensive to get to for battery changes.
Makes sense.
And companies like Wiliot, they're making battery-free Bluetooth tags for tracking assets. Things just get scanned automatically using ambient RF. No more manual scanning.
Logistics, retail, I could see that.
Definitely. And it's being explored for tiny medical implants, on-chip stuff, also smart infrastructure like streetlights. Imagine not having to replace batteries in thousands of those. That saves a fortune, sometimes over $1,000 per replacement.
That's a clear benefit, but it can't be perfect. What are the main limitations, the catch?
Well, the biggest one is that ambient RF, the stuff that's just out there, is unpredictable. It fluctuates. It's not steady like solar, usually, or a dedicated power source.
Obstacles, weather, that affects it.
Big time. Buildings, trees, even rain can mess with the signal. So designing an RFEH system is always a balancing act. A trade-off.
Between what?
Usually it's efficiency versus size versus the range of frequencies it can harvest, the bandwidth. You might want a big, super efficient antenna, but that's just not practical for, say, a tiny wearable sensor.
Right, you can't stick a giant antenna on your wrist.
Exactly. So that leads to a fundamental design decision.
Which is?
Do you rely on ambient RF, the free energy that's already around you from Wi-Fi, cell towers, etc., or do you use controlled harvesting?
Controlled meaning you set up your own transmitter.
Precisely. Ambient is great because the energy is already there, but it's low power and unpredictable. Controlled harvesting, using a dedicated RF source, gives you much more power, reliably, better for applications where you absolutely need it to work, maybe in remote places. That choice really dictates how predictable your system will be and how much power you get.
Okay, so this deep dive really shows RFEH is it's more than just a cool idea. It's a real pathway to self-powered devices.
It absolutely is a powerful enabler.
But success really depends on smart engineering, understanding those trade-offs, and crucially, understanding the physics involved.
Couldn't agree more. And maybe a final thought for everyone listening. If you're looking into this, don't forget that impedance matching network. Seriously, don't skip it.
That crucial missing piece.
Yeah. And also, look into specialized chips designed for this, like the PowerCast P2110B is one example. Yeah. And always think hard about that ambient versus controlled source decision based on what your device actually needs to do.
Makes you think, doesn't it? How many gadgets around you right now could potentially ditch their batteries and just sip power from the air? What would a truly maintenance-free world look like?